Hello, Site 101 students. We are up to learning objective 9, where we will return to the subject of correlations, and we will also talk about something called inferential statistics. As you can see, we've now moved into the appendix section of the textbook. And oops, went backwards there. Okay. Um, what we're going to be doing here is returning to correlations, because when I talked about them in an earlier learning objective, I didn't mention any numbers at all. I just talked about relationships and the purpose of correlation. Well, we have something called a correlation coefficient, which is a number that specifies the direction and the strength of a relationship between two factors or two variables. This correlation coefficient will be a number that ranges from -1 up to +1. So it's going to be in decimal form. You're going to get something like a 0.58 or a 0.32 or something like that. And it may be positive or negative. So correlations are typically stated with, two decimal places. So like I said, like 0.78, 0.35, 0.221 or whatever. And it might be positive or negative. So let's figure out what the positive versus negative means. What does the number actually mean? Well, first of all, the higher the number, ignoring whether it's positive or negative, the higher the number means the stronger the relationship. And higher means closer to +1 or closer to -1. So like something like a 0.9 or a -0.9 would be a very strong correlation. It means that these two variables are very strongly related or associated. Something like a 0.1 is a lot closer to 0. So that would be a very weak relationship between two variables. So we look at the value of the number. 0.9 is stronger than 0.6. 0.6 is stronger than 0.3. 0.3 is stronger than 0.1. And what about if we get a 0? What do you think that means? Well, okay. Trying to give you a moment to answer, but I guess I won't hear you. Anyways, a 0 would mean basically no relationship exists between the variables. So why do we have positive and negatives? Well, let's look at why. Okay, first of all, before I leave the screen, so just to make the point clear, if I had a negative 0.5 and a positive 0.5, they are equal strength, okay? So you ignore positive or negative when you look at how strong it is. So what does the positive and negative mean? Let's go to these pictures. Here is an example of a positive correlation. Okay? Positive correlation indicates that as one variable increases or goes up, so does the other one. Similarly, if one goes lower, so does the other one. A positive correlation means same direction. And I'm actually doing something with my hands now that I always do in class. I hold them, when I talk about positive correlations, I hold both of them facing like the ceiling, or I turn them down both facing the floor to show that the variables are, move in the same direction. Low scores go with low scores. High scores go with high scores. Here's an example of a positive correlation. They looked at the percent of classes that students attended and their psychology exam scores. So as you can see, if people attended more classes, as you move to the right along the bottom, that's attending more classes, well, then you move up to where the dots are, and they scored higher. People that attended more classes tended to score higher on the psychology exam score. This graph that's shown here is called a scatter plot. Scatter plot. Each one of these dots is an individual subject or individual student in this case. So we can see that there's one guy that's kind of down near the bottom right that doesn't really fit the pattern. We call that subject an outlier. Excuse me, outlier. I can hardly talk anymore. I'm too tired. Anyways, because he's not really fitting the overall pattern, but that happens. People just like we expect tall people to have bigger shoe sizes, but every now and then you find some tall guy with really small feet. But so you get these outliers occasionally. That line that is drawn, that is computed mathematically, like a computer actually computes where that line goes. It is called the line of best fit. It is the line that best represents the data. And when you have a positive correlation, the line of best fit will always be sloping up to the right. And every time you have positive correlation, it slopes up to the right, which gives you higher scores going with higher scores. If you look at the right side of the graph, if you look at the left side of the graph, low scores, low percent classes would go with lower scores. What else do I want to say? Okay, let me look at my notes. Okay, I think that's about it. So this is a positive correlation. We have the line of best fit. It's called a scatter plot. Each dot is a subject. Moving on. This one is a negative correlation. When you have a negative correlation, you will always get a downward slope, downward towards the right. Because once again, I'm going to do that thing with my hands that you can't actually see. I got one hand pointing up, one pointing down. As numbers go up on one of the variables, they go down on the other, opposite direction. So positive correlation was always the same direction. Now, if I get higher, let's say this one's number of beers drank versus score. Somebody that drinks more beers, they get a lower psychology score. If they drink lower number of beers, so I'm going down, then they get a higher psychology score. So my hands are going in different ways, whichever way I phrase it. So you always get this downwards right slope. And what else? And hopefully these both make sense. If you attend more classes, you tend to do better in a course. If you drink more beers, I don't know how they're measuring this in this particular example. Maybe it's the night before, maybe it's the week before, who knows? But and I'm also wondering why does every single student at least one? Isn't there any student that didn't drink any beers? Okay, anyways, that's besides the point. But this is negative. This is what the positive versus negative means. It tells you the direction of the correlation. Do high numbers go with high scores, or do high numbers go with low numbers on the other variable? And so when you read things in an article, like a journal article or in a textbook, they might say things like, this variable was positively correlated with this other variable. Positive doesn't mean good or bad. When you hear negative correlation or positive correlation, nothing to do with good or bad. It's just about direction. Okay? Because I've heard students often interpret, they hear negative correlation, they think it's a bad thing, like, oh, it's a negative outcome or something. Well, no. I mean, this one turns out to be these guys that drink a lot of beers aren't scoring very well. But okay, so now we get to the zero. And this is an example of a zero correlation. This is what the scatter plot would look like, and the line of best fit would look like. These dots have no discernible pattern. This is, once again, this line of best fit is mathematically computed. If it's a straight line or something close to a straight line, that means that there is no correlation, or there might be a tiny correlation if it's just not exactly straight. And this makes sense because here they're looking at the students' shoe sizes versus comparing and correlating them with their exam scores. And it turns out that your shoe size has no relationship to your final exam score. You're just as likely to score high or low no matter what your shoe size is. Okay, let's keep going. it's a flat line. Okay, this is returning to a very something I introduced earlier. We've already talked about the TV viewing and teenage obesity. I'm just going to go up to the top left, excuse me. And I just wanted to present these examples. They were actually, I don't exactly remember, I've had them for years, but I got them from one study or another. But they found that the number of hours studying per week correlated with test grade was significant at 0.35. It's a positive. So when you read this, when you see this right away, like imagine you're reading it in the textbook, right away, as soon as you see the number, you know what this means. Oh, more hours of studying led to higher grades because it's a positive correlation. So you know that they're going in the same direction. And then the second one is number of hours drinking per week. And I'm sure they're talking about drinking booze, obviously. In the test grade, this was also significant, negative 0.8. Oh, it's negative. So more drinking led to lower test grades. Right away, if we were in class, I'd ask you which one of these is stronger. And I'm sure you're all good critical thinkers and you've been paying attention, and you would all yell out that negative 0.8 is stronger than 0.35. It tells us that that's a stronger relationship between those two variables. So, drinking, the amount you drink is more related to your test grade compared to number of hours studying. Okay, let me check my notes. Oh yeah. Once again, remember these are correlations, so we're not assuming any causality that one thing causes another. So you may right away come to the conclusion, oh, if you drink too much, your test grade will tend to go down or tend to be lower. Well, remember, it can go in the opposite direction because it's a correlation. So maybe people who generally score low anyways, they're like, what the heck? I may as well drink a bunch. So like it may be that they've been scoring really lowly on past tests, and so they decide to not even try to study. They drink more. And so it could be we still have the directionality problem. And you may say, well, it's based on, one test grade. So like the drinking must have come before it. But if you can assume that there was previous incidents, then you can't make that case. Like there may have been other tests in this class, before this one. And so they may have a pattern of scoring lowly, and this has led them to drink more before it was measured in this correlation. Like, it may have been the test results that caused them to increase their drinking. So once again, we have the directionality problem, and there might be a third variable problem in this as well. I didn't really think of an example, but that's always possible. Okay, this is what a correlation coefficient is. This is what the numbers mean. The second topic in this learning objective is inferential statistics. Inferential statistics allow us to determine whether we can generalize our findings from our sample to the population. And this is the goal of every research. Like I talked about that weight loss pill. I mean, I had 200 subjects. My study wasn't to improve the lives of those 200 people. It was to find a pill that would improve the lives of the whole population I was interested in, which would be millions of people possibly in the States. And so in order to say that, in order to generalize and say that what I found in the study will also be true for others, you have to have what's called statistical significance, as it says on the screen here. So you cannot generalize your findings unless you achieve statistical significance. Statistical significance basically means that the results are not likely due to chance. So you have to arrive at the state where the numbers say that it doesn't look like it's a fluke. It looks like your independent variable really did cause an effect. on the dependent variable, which means my weight loss pill worked. So the way statistical significance works is that it calculates what are the odds that you could arrive at the numbers you did if your pill did not work. And so you want that to be really low. I'm going to show you in a chart. And I made this chart up myself. It's not in the book. And these are just made up numbers. Okay. They're just to illustrate a point. So let's say we're going to look at three different situations where I ran my weight loss study. And we have on the left, we have the experimental group. They're the ones that got the weight loss pill. And after however many days, let's say I did it for 2 months or 4 months or whatever, on average, they lost 10 pounds, the group on average. And we're looking at the first line across. Now, the control group, they didn't get the weight loss pill, they had a placebo, but they lost 8 pounds. They're pretty close. There's only a 2 pound difference between the groups. So when I put these numbers in, and it's more complicated than just these three numbers. The statistics look at the numbers from every single subject. But when I put the numbers in, let's say I arrive at a p-value of 0.75. The p-value is always going to be a decimal value, and it represents the probability of getting a 2 pound difference, whatever the difference was between the groups, in this case, 2 pounds. What's the probability of finding a 2 pound difference if my pill had no effect? Well, you know what? 2 pounds isn't a lot. It's probably very common that if I did, even though my pill had no, even if my pill didn't do anything like that, it's quite likely that one group's going to lose 1 or 2 more pounds than the other group. And so it turns out to be a very high p-value, 0.75. What that means is that there's 75% chance that I could arrive at these results without the pill working. I could be like saying, well, look, they lost 2 more pounds, but there's 75% chance that a group would do that anyways, even without the pill. So obviously, I'm not even close to concluding that my pill worked. It's most likely, this is telling me it's most likely just a fluke result. Let's look at the second line. Now it's a little bit better. There's a 5 pound difference. The control group only lost 5 pounds. So there's 5 pounds difference. This seems like a pretty good difference. The p-value ends up being 0.25. Tells me there's a 25% chance, only 25% chance of arriving at these numbers if my pill didn't work. Well, you know what? That's not good enough. I mean, 25% chance, like I'm not going to start manufacturing this weight loss pill and spending millions of dollars if there's a 1 in 4 chance that it didn't actually work. Your p-value has to be much lower. How low? Well, how low? In psychology, we're looking for a p-value of less than 0.05. And I kind of alluded to this earlier in another learning objective, which means a 1 in 20 chance. It has to be less than 0.05 in order for you to say that you found a statistically significant result. So this last bottom row indicates this. The experimental group lost 10 pounds. The control group only lost 2 pounds during the same time frame. The 8 pounds difference is significant. Like you feel that. Like, that's 5 times as much weight that the experimental group lost. Even before I see the p-value, I think, oh, this looks pretty significant. The p-value ends up being 0.03. That means I go, hey, hooray! I have found a statistically significant difference. I can conclude now that my weight loss pill actually affected weight loss, that my independent variable affected the dependent variable. I can't conclude that in the first two examples, but when that number gets less than 0.05, it means that there's less than a 1 in 20 chance that it was just a fluke result. That means that there's over a 95. In this case, there would be a 97% chance that my pill worked. In psychology, we're willing to go with that. We want over 95% chance that the experiment worked before we declare it a success. So these are fairly rigid. I mean, overall, they're rigid standards. You have to get up over 95%. I mean, the p-value has to be very low, but this is the way science works because results have meaning. Like people start, such as a weight loss pill. I mean, a company might spend millions of dollars if they think it worked. By the way, if it was actually something like a drug, they would want a p-value less than 0.01. They wouldn't even accept this because it'd be too risky. It might interfere with people's health, and like so. Depending on the level of importance of your study, sometimes certain studies use a 0.01 level, which means there has to be less than 1% chance of a fluke result. But for most psychology studies, it's 0.05. And this is a huge deal, like, because um, the getting the p-value less than 0.05, that's what allows you to publish into a journal. That's what allows you to do a poster presentation or to give a talk. These first two incidents, they've shown nothing. You can say, oh, they lost 5 more pounds in the middle there. Well, that's nothing. A p-value 0.25. You have to reach statistical significance before anyone takes your results seriously. And it can be just so aggravating after sometimes months of work of setting up an experiment, bringing hundreds of subjects in, and then it all comes down to the final calculation that computer does, and you get something like a 0.07. You basically are throwing your experiment out. In that case, you would say, okay, there's something here. I'm gonna redo it and change, maybe try to clean it up or get more subjects, or you try to, figure out how you can get a little closer, because it would be encouraging if it was just above 0.05. But you really, it's like night and day. 0.06 is garbage. A 0.04 is publishing in a journal, and this is a way. Once again, this is a way. Most scientists work that they use any kind of experiments or thing. They want you want to err on the side of caution, even though like a 0.07 would mean, oh, that still probably worked. It's not good enough for people to start changing manufacturing things, or like putting like maybe a government program is going to be based on your results, because you found something that benefits school children, or like some results are really important. So this is why we have a stringent standard, where you have to feel really sure that the result works. And remember, I talked earlier about replication. If you redo the experiment, it becomes you become much more sure if you get a second significant result. So that is what statistical significance means. That is what inferential statistics is used for. Inferential statistics is the method of calculating statistical significance. Okay. Um, I think that's it. That will conclude learning objective 9. Oops. Okay.